we can extend the applications of derivatives to implicitly defined functions. So remember where we had an implicit function and differentiated it. So where we had x terms, we can differentiate it directly with respect to x. And for the y terms, we differentiate using the chain rule. And then solve the resulting equation for dy dx. So if you're given some point xy, and not the graph of the implicit relation, then you can basically substitute these into the derivative. And if the derivative is 0 or does not exist, then you have a critical point. And similarly, if it's greater than 0, the function is increasing, and less than 0, the function is decreasing. And if you differentiate this to obtain a second derivative, and as we've seen, this second derivative may depend on x, y, and the first derivative. And similar to the explicit functions that we've been dealing with, this derivative gives us information on concavity. So if it's greater than 0, then this behavior at the specified point is concave up, or we have a local minimum. And if the second derivative is less than 0, we have concave down and a local maximum. And if the second derivative is 0, we have an inflection point. And now we'll cover some worked examples. Determine if the implicit relation is increasing or decreasing at this point. Well, if we differentiate this implicitly, we have 3y squared by dy dx minus 2x is equal to 0, and therefore dy dx is equal to 2x on 3y squared. And if you substitute for x equals 1 and y equals cube root 2, then you're going to get a positive derivative. And because the derivative is greater than 0, then the function is increasing. Let's determine if the curve given by this implicit relation is concave up or concave down at this point. So if we differentiate implicitly, we get 3y squared dy dx is equal to 2x, and therefore the derivative is 2x on 3y squared. And then differentiating again, we can use the quotient rule. So we have 3y squared by 2 minus 2x by 6y dy dx. And that's divided by 3y squared, all squared, which is 9y to the 4. And now you can substitute for x and y to get the derivative, and then substitute for x, y, and dy dx. And from that you can determine if the curve is concave up or down, and post your answer in the comments. Let's find the equation of the tangent and normal lines to the curve at x equals 2 and y equals 5 to the third. Well, the general equation of a line is y minus y naught is equal to the slope by x minus x naught, where x naught y naught is a point on the line. So therefore, if you differentiate this expression implicitly and substitute for x and y, you're going to get the slope of the tangent line. And if you take a point on a line, so that would be this point, which is at x equals 2 and y equals 5 to the third, then you can write the equation of the tangent line in the form of y equals mx plus c. And for the normal line, which is perpendicular to the tangent line, so the slope would be the reciprocal of the negative of the slope of the tangent line. And think about why that is, and post your answer in the comments. Does y of x have a minimum or a maximum if the derivative is equal to y cosine x, and y at x equals pi on 2 is equal to 2? Well, if we substitute for pi on 2, what we get is y of pi on 2 is equal to 2, and that's multiplied by cosine pi on 2. So this is equal to 0, and therefore it's a critical point. Now if we take the second derivative, so that's equal to y by minus sine x plus dy dx by cosine x by the product rule. And at pi on 2, dy dx, as we've seen, is 0, so this term's 0. And the first term is y of pi on 2, which is 2, multiplied by minus sine pi on 2, which is minus 1, so that gives minus 2. And because the second derivative is negative, the curve is concave down at this point, so the critical point is a maximum.